So we can go to the next presentation. The next presentation will be given by Willem Uyttendaele and Ruben Geerinck from Centexbel in Belgium, from Ghent, very beautiful town. So Centexbel is a research center dedicated to textile applications, so developing materials and methodologies for producing textile packaging in this project. Please.
Okay, thank you, Beatrice. So for my presentation, the goal will be to give somewhat of an overview of the results that we had as Centexbel within the Bio on Top project. So I will start with a short introduction on Centexbel, who we are, continue with some of our development in PLA-based coatings, and after that, my colleague Ruben will take over with some of the developments on PLA-based yarns for the tea bag applications. So first of all, Centexbel, a very short introduction on who we are. So we are a collective research and technical center located in Belgium, with a big focus on the textiles and plastics converting industry. So we have about 3 sites located spread around in Belgium, and about 180 people working there. We have different well-equipped testing laboratories for physical, chemical, fire, and microbiological tests for both plastics and textiles applications. One of the maybe more famous examples now is certification of COVID mouth masks. So this is something that, for example, happens at Centexbel. And then next to these testing laboratories, we also have different sites for pilot platforms. On the one hand, for extrusion, different also weaving, knitting of textiles, and then also coating and finishing of different textiles. So really the whole conversion of a material into a finished textile or plastic. So then for the Bio on Top project, like I said, I will kick it off with the PLA coating developments. So I was planning to start out with a slide on what is PLA, but I think after these 2 beautiful presentations already, we all know what PLA is. So I will just continue with the developments itself. So within the Bio on Top project, the goal was for the PLA coatings to work to 2 different demonstrators. One of them is a textile-based food wrap, for which the goal was to apply a PLA-based coating on a PLA fabric, or use a PLA-based coating to laminate onto this kind of a fabric. And then the second demonstration is some kind of a shopping bag, where once again, we want to apply a PLA coating on a PLA substance, for example, crosslinkers and so on, improve durability. Since we also want these items to have a nice look, we also looked into methods of printing this bio-based and PLA-based material onto those different substrates. So to start out, how do we actually make PLA coatings? So when we started this development a few years before even the start of the Bio on Top project, there were not really a lot of options. There was one commercial product by Toyobo, which was a PLA that was modified to be soluble in water, but it was expensive. It was not fully bio-based. It took a lot of solvents to do this modification. And in the end, the company quit the sales because the sales were just no longer there. And so it's no longer available. And then the second option we had, and yeah, kind of the only option, is to just start from the PLA granulate and try to turn it into a coating. And here we took some inspiration from a PVC plastisol. So maybe shortly for those who are not aware what a PVC plastisol is. So a plastisol is a combination of a powder and a plasticizer. This is commonly done for PVC For example, coated textiles, for artificial leather, there are a huge number of applications of PVC plastisols. And we thought maybe we can do the same for PLA. We can grind the PLA down to a powder, mix it with a plasticizer, treat it in an oven so that the two components fuse together, and we have a beautiful coating. Of course, it was not that easy. Just mixing a PLA powder and a plasticizer was not enough. We also had to incorporate some water to essentially dilute the two components and obtain a formulation that is actually coatable and processable. But if we mix these three components with some pepper and some salt to really get a nice formulation, then we can use this kind of process to actually coat PLA. And then we arrived at what we then called our bioplastisol or PLA plastisol, which contains about 40% of solid content. So this 40% includes both the PLA and the plasticizer and about 60% of water. Since we can make it in quite an easy one-step process, we just mix the components together. It's relatively cheap and we don't have to use any organic solvents. So it's completely free of organic solvents. The only solvent we need is water. Then for the bio-based content, since some of the plasticizers we use are not fully bio-based or not fully bio-based yet, we arrive at 75 to 90% plasticizer depending on the application. Then also this formulation is compatible with different fillers, with colorants. I mentioned we also looked into printing, so colorants are quite important. And we can fuse it for 3 minutes at 160 degrees to obtain a coating. So since this development was quite nice, quite novel, we also applied for a Textile Innovation Award this year, and we actually won it in the category of new approaches to sustainability and circular economy. And then, now we have this quite nice formulation, and then we try to use it as well within the Bio on Top project, both for direct coating applications and for screen printing applications. And then once we have these materials, we also looked at, of course, because we're in the Bio on Top project, we looked at some biodegradability, because according to some articles, plasticizers can have quite a big influence on the biodegradation of some materials. And so we just prepared a 150 micrometer film using these coating formulations and then evaluated the home compostability at OWS. And here we saw that under home composting conditions, we see that the material disintegrates in 6 months at 20 degrees, which is what you need for the home composting. But when we look at CO2 conversion, then we are actually quite lacking. So we see that even after almost a year, that not even 20% of the product has been degraded into CO2. So we see there is some effect on the biodegradation from the plasticizer, but it's not enough to really kick off the PLA into a product that is home composting using just the plasticizer. But of course, it remains industrially compostable. The disintegration speed and this conversion speed into CO2 will also somewhat depend on the type of plasticizer we use, the addition of crosslinkers and so on. So we're able to somewhat tune the durability of these kind of materials by varying the plasticizer and the crosslinker. And then we also use these materials as either coatings or inks. And since recently I also added it on the slides, we can do it also with PHA, so not just PLA. But within the Bio on Top project, we mainly used PLA. And we see with these coatings that they have a good UV stability, they have excellent abrasion resistance. So if you're familiar with the Uyttendaele test, we can do about 100,000 cycles of rubbing with minimal weight loss, so it's really quite excellent. The coatings and prints have good flexibility, so it's not excellent, it's not very elastic, but the flexibility is still quite good, especially for a PLA, thanks to the plasticizer we add. Then also we can improve some of the visuals and the touch by actually working with a two-step process. So I mentioned beforehand, we just fuse the coating at 160 degrees for 3 minutes. But if we do a calandering or a heat press step afterwards, then actually the surface of the coating or the print will be much smoother. The properties will somewhat improve as well. So this is also an option for these kind of materials. Then, as I mentioned last slide, the biodegradation can be tuned using different types of plasticizers and either including the crosslink. Then we also looked at the washability, because of course, if we look at some kind of a food wrap, preferably we could just wash it after we've used it and not having to just clean it manually. So that's why we look at washability for these materials. And you can see on the bottom left, 2 samples, in this case a print, because it's usually easier and more visual to evaluate the washing on a print. You can see on the left that if we use no crosslinker in this formulation, that quite a lot of the print washes off. However, if we add a crosslinker, then we see that even if we wash 10 times at 30 degrees, that most of the print is still there. There is, of course, definitely a difference with the print that hasn't been washed, but the difference is quite minimal. Then the second route within the project was to use hot melt coating. So instead of using this water-based process, what we try to do is we melt the PLA down to a very low viscosity and then apply it as such on the material. The difficulty here within the project is that we are working with PLA-based fabrics and we are trying to coat it with PLA. And this means that when we try to coat, we have to stay below a processing temperature of 140 degrees, because otherwise we will damage the fabric. And for this reason, we also looked at the partner Total Corbion and asked at the time what the lowest melting point or the less viscous PLA grades were, which were the Alex 930 and 975. So that we could try and see what the effect is on the viscosity if we would get that low enough with these kind of materials. We then included 10% plasticizer to increase the flexibility, decrease the processing temperature of these materials. And then we measured the viscosity using Brookfield, and you can see the graph here on the slide, with the red line being the limit for this hot melt application technique. So with hot melt, you really need quite low viscosity of about 80,000 centipoise at maximum. And we see that with these materials, even when we add different types of plasticizer, that we still arrive at a processing temperature of about 180 degrees using the hot melt coating technique. So when we want to use these materials to coat PLA, it's not really suitable. However, we did try them as well then with, for example, cotton or linen fabric, which are also natural and don't have these issues with temperature. And then we saw that with these materials, we get very good properties regarding barriers, regarding abrasion, and regarding the flexibility as well. But since we're in the Buy on Top project, we really wanted to focus on these PLA-based fabrics. And for this, we then used an experimental, very low viscosity PLA grade from NatureWorks. So this is a grade that starts to melt already at 60 degrees. And then we added 10% plasticizer to it as well. And then once again, you can see a graph here of this experimental PLA grade. You see without plasticizer, still we have a processing temperature of about 160, 150 degrees, which was too high. But once we added 10% plasticizer, thanks to the lower melting processing and also the improved flexibility, we could in the end process this material at only 110 degrees, allowing it to coat it on a PLA fabric without damaging this fabric whatsoever. So then what we did in the end, we applied at 120 degrees and we coated this material on a PLA fabric. And we then also used this hot melt technique to laminate a PLA film supplied by Aimplus to the PLA fabric, which was supplied by Siun, another partner within the project. And then we evaluated the properties of these materials. And when we looked at just the coatings, we see we have quite a decent liquid repellence with a score of 4 out of 8. We have quite a good abrasion resistance. However, the issue with this material is that it remains tacky. So I mentioned we're using a relatively amorphous PLA grade, we're adding plasticizer into it. And this meant that even at room temperature, the coating remained tacky, which means that for the applications within the Buy on Top project, it's not really suited. However, when we use that to laminate the PLA foil, of course, you don't feel the tackiness anymore, and it's actually preferred to have some remaining tack even at room temperature, to ensure the adhesion. And so when we laminated the PLA foil to the PLA fabric with this kind of material, we saw an excellent liquid repellence thanks to the PLA foil and a good adhesion as well to the PLA fabric. And then I will pass on to my colleague Ruben, who will continue with the tea bag development.
People are waiting to go. I think we can go on and wait to come.
Okay, so also from my side, good morning. Another demonstrator we looked at in the Bio on Top project is a tea bag, where it makes sense to make it home compostable, as it is very it's intimately mixed with food, so you cannot recycle it. So therefore, to avoid the incineration, it is very useful that it would be home compostable. Now, we started with our monofilament extrusion, so it's a woven tea bag for the higher class tea bags, not a non-woven. So we start with the melt extrusion process, where we have a pilot monofilament extrusion line, where here at the site you can see the extruders. We have 2 extruders. We can use different quenching techniques, and then we have 3 heated ovens to do the stretching of the filament and to get the strength into the filament. You can get speeds up to 200-250 meters a minute, so it's quite low production speeds, but it's also pilot line, so it's not industrial scale yet. The goal now, however, we got some properties that we need to reach from our project partner Siyun, that is currently making PLA-based woven tea bags, but of course for them it would also be very interesting to make it home compostable. So we need to make a very fine monofilament yarn, 3 grams for 1 kilometer of yarn, a strength of 35 centimeters per tex, and most importantly, home compostable. So we tried blending with different polymers, so the PLA with PCL, with PHA, PBS, PBSA. As we already saw in the other presentations, it's coming down to the same polymers to try and find something that is home compostable. First, looking towards the mechanical properties of the yarns that we produced. So here we have the 3 different categories. You have the PCL, the PHA, and then the PBS, PBSA blends. Where here on the left, you can see the virgin PLA, which achieves quite good mechanical properties. In blue, you have the strength, and in orange, you have the elongation. And when we add PCL in low, medium, or high concentrations, you can see that the strength of the filament is dropping when adding a larger amount of PCL, of course. PCL is a low melting polymer. It's, I think, 60 degrees. So therefore, you also see the elongation going up a little bit, and processing becomes more difficult with the higher concentrations of PCL in there. The second type of polymer that you tried is then the PHA materials, where you can see that the type of PHA is very important towards the processing and the mechanical properties. You can see for PHA1, for example, we only get a strength of 30 centimeters per tex, which is a quite severe drop. But PHA2, we can maintain the properties of the virgin PLA. So there, the choice of PHA is very important. And then the last one is the PBSA. But that was very difficult to process, as this is also a more sticky material and a more flexible material. It is less suited for filament extrusion. However, we could manage to make some yarns out of it to be tested, but processing was quite difficult there. If you then look to the home composting trials, again performed by project partner OWS, home composting in 28 degrees Celsius, and it should be biodegraded within 1 year. And here we can see that, again, we found some formulations containing PLA, PCL, and some pepper and salt. some others than my colleague Willem, that we can achieve some tunable biodegradation with a different lag phase. So for example, so we have the blue curve is the reference, the green curve is the virgin PLA material, and in between we have different formulations that can reach the home compostability mark with different onsets of biodegradation. For the one compound here in red, it's only after 120 days that it will start to degrade. This compound, however, will not get certified as home compostable because it was not within the 1 year. But in the end, after let's say a year and 1/3, we get that home compostability nonetheless. So this is quite interesting results that we can produce a home compostable yarn with the right mechanical properties. Other important properties when developing a yarn for a tea bag, of course, is the shrinkage, as it needs to withstand 100 degrees of the water of the tea. And here you can see in the graph that for the PLA and the low concentration of PCl, you have a shrinkage of about 20%. For the higher amounts of PCl, this becomes more problematic, and you go up to 35–40% of shrinkage, which is quite high. So it's, we need to check whether this will give an issue towards the final tea bag application. The weavability is also tested, so all the different formulations that we tried, we sent some bobbins to Sioen, where they are tested at industrial scale, but only in weft direction. And here you can see a picture of such a trial where they produce small amounts of fabric, where for some you can see a very good aspect, but for, I don't know whether it's clear in the picture here, but where you can see that, for example, for the number 3, you get visually some streaks. It's not that nice of an aspect in the fabric, so that is something to be worked on with some of these compounds. Now the pilot scale is done, so Sioen is now performing the first industrial scale trials to see whether they can match the properties that we reach and to be able to produce 100% tea bag out of these formulations. So hopefully by the end of the project in the next 6 months, we will be able to develop that tea bag and present that at the end of the project. Now, for a conclusion, for the coatings, we can prepare PLA coatings using different methods, but they must be formulated, or the formulation must be tailored to the specific application requirements that are needed. For the yarns, we have a home compostable yarn, and that is now in evaluation on the industrial scale is now ongoing at the moment. So hopefully that will end by the end of the project. Thank you very much. That was it.